So we're going to go back to talking about the pizza recipe again. 1 crust plus 5 ounces of sauce plus 2 cups of cheese makes 1 pizza. And earlier we talked about what would happen what could we do if we had 10 cups of cheese. Now we're going to be a little more specific and say we have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce. How many pizzas can we make? One person saying 3. Yeah, the answer is 3. How do we figure that out?
The tomato sauce, because you can't do 5 cups of cheese and 10 cups of cheese, it's times 5. But
Right.
It doesn't have enough tomato sauce to do that.
Right, so this is the one we're going to run out of. And because these are real objects and small whole numbers, we can do the math in our head, and it's easy to think about. Right, we look at this and, well, we could make 4 pizzas out of that, and we need 2 cups of cheese, so we could make 5 pizzas out of 10 cups of cheese. With 15 ounces, we need 5 ounces for each pizza. We can only make 3 pizzas. And we understand that once we made the 3rd pizza, we have to stop because we ran out of sauce, right? We're going to apply the same thought process to a chemical reaction, okay? So just keep your brain going. First, we're going to show how we would write this out, showing our work to figure this out, because that's what we're going to do with the chemical equation. So we have 3 different reactants, 3 different ingredients. What we want to do is find out, we're going to show on paper or on the screen, how we figured out that 4 crusts will make 1 pizza. And this is very similar to what we did yesterday, Monday, except we're doing it for all the ingredients now. If I want to find out how many pizzas I can get, I need to multiply by a conversion factor, right? If I'm trying to find pizzas, I put pizzas on top and I put crusts on the bottom. And how do I know the ratio there? It's in the recipe, right? I get 1 pizza for 1 crust. 1 crust gives me 1 pizza. And so we say, well, that's kind of silly to even write that out, but it's practice. Okay, well, 4 pizzas. Make that plural. We did the 10 cups of cheese one already, but let's just do it again. Again, we're trying to figure out how many pizzas, so we'll divide by cups of cheese. And this ratio also comes from the recipe, the equation. 5, wait, where's my brain? 2 cups of cheese to 1 pizza. These numbers right here. 1 pizza, 2 cups of cheese. And those units cancel out, and that gives us 5 pizzas. And then we have the sauce. 15 ounces of sauce. And we're going to put in another conversion factor ratio here. And this is going to relate pizzas to sauce. We're going to look at this recipe. For 5 ounces of sauce, we get 1 pizza. So 5 ounces of sauce for 1 pizza. Would it be true to say we can get 5 pizzas from 1 ounce of sauce? No, that's ridiculous, right? Nobody would think that. When we get to chemical equations, though, sometimes your common sense just is gone because the objects are not familiar. So just remember that you're finding the number in front of whatever unit you're looking at, 5 ounces of sauce, down here, 5 ounces of sauce. 1 pizza, 1 pizza. We're taking these individual pieces of this equation, this recipe. I guess that one's kind of long. We can pick any 2 of those boxes and make a conversion factor. Everybody okay with that? I should finish this down here. So that is 15 divided by 5, 3 pizzas. These units work out as well. So when we're identifying how many pizzas we can make, how do we choose between 4, 5, and 3? Do we pick the one we run out of ingredients first? So the smallest one, right? Because when we've made 3 pizzas, we're out of sauce. Can't make pizzas without sauce. So it stops. This is what we're going to do with chemical reactions. We're going to take the amounts of ingredients, of reactants that we're given. We're going to convert them into the amount of product that could be made if we were able to use it all up. And we're going to get more than one answer here, and then the one we choose is the smallest one. Okay. Sometimes students want to add these up. It's very creative, but can we make 12 pizzas with this stuff? No, we can only make 3. Any questions? Anybody want pizza for lunch? I do. Pizza for breakfast is pretty good too. So here it is in pictures, right? The 4 crusts can make 4 pizzas. 10 cups of cheese could make 5. This is our limiting reactant or limiting ingredient. This is only going to make 3 pizzas. So this one limits the production. It limits our product. So we call the tomato sauce the limiting reactant or the limiting reagent. It's whichever reactant makes the least amount of product. The maximum number of pizzas we can make, which is the smallest number of those choices that we ended up with, is called the theoretical yield. Because we should be able to make 3 pizzas, but does anything ever go wrong when you're cooking? I mean, if it says you're supposed to be able to get 5 dozen cookies, do you always get 5 dozen cookies? I don't. Partly because I eat a lot of the dough, but stuff happens. But that's the theoretical yield, right? So in a chemical equation or a chemical reaction, the amount of product is also limited by the limiting reactant. One of the reactants is going to run out. Because in the kitchen, if you go to make pizza or bake cookies or something, do you ever have exactly the right amounts of everything? No. If you're going to go make cookies, you might run out of eggs, but you've got like lots of flour and sugar left, right? And it's in chemical reactions as well, it's very unusual to have just the right amount of everything. That happens when you've got like a salad kit, right? And you just put everything in there and it's all perfect. But that's an unusual situation, right? Same thing with chemical reactions. There's a lot of words on these slides. So when we have a chemical reaction with multiple reactants, one of those is probably going to get used up. Just like with the sauce, we use up one of the reactants, the reaction stops, no more product. The reactant that gets used up is the limiting reactant, and it limits how much product we can make. The other reactants are in excess. We have extra of them. And what happens to them? What happens to the extra cheese and the extra crust when you're making pizza? It just sits there, right? It's still there. If you could find more sauce, you could make more pizza. But it's just going to sit there. The excess reactants are also just going to sit there. Nothing's going to happen to them. They're just going to be in the reaction mixture. So we're making pizzas, and maybe we got distracted by Candy Crush or something, or YouTube, and we didn't hear the timer, and we burned one of the pizzas. And we burned it bad. Nobody's going to eat it. So now we only have 2 pizzas, even though we should have been able to make 3 pizzas, right? Or maybe we dropped one on the floor, or the cat jumped on it or something. That's our actual yield. It's how many we actually make. And in a chemical reaction, typically we don't get the theoretical yield. We get an actual yield, which is less than the theoretical yield. So we use percent yield to express how efficient the process is. Now, if you're baking pizzas for a living, you're going to want your efficiency to be close to 100% so that you're not wasting a lot of ingredients, right? So percent yield looks at how much was actually made in reference to how much you theoretically could have made. We take that ratio or that fraction and multiply it by 100 to get a percentage. Closer to 100 is better, right? This is kind of a nice summary slide. It's got all the words. Limiting reactant, the reactant in excess, the theoretical yield, the actual yield, the percent yield. All just kind of defined for you right there. So let's apply this to a chemical reaction. So we were looking at this reaction of methane with oxygen. So methane burning, and we see that with one molecule of methane, it requires 2 molecules of oxygen and will produce 1 molecule of CO2 and 2 molecules of water. So this equation implies that every 1 molecule of CH4 reacts with 2 molecules of oxygen. So it's kind of like the pizza requiring 2 cups of cheese. What if we have 5 molecules of methane, CH4, and 8 molecules of oxygen? What's going to happen? We're going to do the same process that we did with the pizza. So we're going to take the first ingredient that we have information about, the 5 molecules of methane. So if I have 5 molecules of methane, how much CO2 could I make? Well, I'm going to get 1 mole or 1 molecule of CO2 for every molecule of methane. So I multiply there and I get 5. Then I have to look at the other ingredient and see how many product molecules can I make from that one. So 8 molecules of oxygen, I get 1 CO2 for every 2 molecules of oxygen. And so from this amount of oxygen, I can only make 4 molecules of CO2. Does that make sense? It's like the pizza. So when the 4 molecules of CO2 are made, we've run out of oxygen and the reaction stops. And what happens to the extra methane? It's still there, but it can't react because we ran out of oxygen. So oxygen in this case is our limiting reactant. Our theoretical yield would be 4 molecules of CO2. Any questions? So this is sort of the big picture master plan for doing calculations like this. This is what your book suggests, and there's nothing wrong with it. It's just not my preferred method. They say, well, take all the ingredients that you have, go grams to moles of product, and then stop there and look at which one of those is smaller. Take the smaller one and convert that into mass. So that's fine. You can do that. But this is what I find works better. It maybe takes a little more time, but it takes less thinking. And so I think that's a good thing. So just go ahead and go to grams of product, mass of product. And here, just continue on and find mass of product. And then just choose the smaller one and be done. So you get 2 answers. Choose the smaller one, and that's the amount of product that can be made. So let's test that out. Ammonia can be synthesized by this reaction. What's the theoretical yield of ammonia in kilograms that we can synthesize from 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen. Well, we read the question. Now let's take the numbers, the amounts that were given, and write them under the balanced chemical equation. So it says I have 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen. And they're asking, what's the theoretical yield of ammonia? That's this guy over here, the product, in kilograms. So here we have two reactants, and we're given amounts for both reactants. So just like with the pizza where we have the different crusts and sauce and stuff, we have to look at each of these separately and see, well, how much ammonia could I make from 5.22 kilograms of hydrogen? In a separate calculation, I'm going to find out how much product I can make from 31.5 kilograms of nitrogen. I'll end up with two answers, and I just choose the smaller one. So that's the overall idea. So grams to moles to moles to grams. I'm going to do that twice. Now this one, we've got this kilogram business. There's different ways that you can handle this. We did an example at the end of lecture on Monday where I think we had with kilograms or milligrams or something. And it was at both ends, and we realized, oh, those are just going to cancel out, right? So let's do this. We're going to do the hydrogen first. So I'm going to write 5.22, and it's kilograms. I'm going to write the kilo in red. So it's kilograms of hydrogen. Remember, kilo stands in for times 10 to the third. So K equals times 10 to the third, which is a number, right? So what I'm going to do is I'm just going to leave the kilo there and sort of setting it aside and say, I'll deal with you later. And I'm going to take this blue gram and I'm going to cancel the grams, and I'm going to go on and just do this in grams and deal with the kilo part later. Everybody okay with that? So after grams of hydrogen, I need to go to moles of hydrogen, right? I'm going grams to moles. I'm going to moles of my product. They're asking about NH3, so that's what I'm trying to find. And then I'm going to go to grams of NH3. Remember, I'm just ignoring the kilo for right now. So I'm going to put grams of H2 down here and moles of H2 and moles of NH3. I'm going to make sure that my units cancel out. So this grams cancels grams of hydrogen. It does not cancel the kilo. It's still sitting there. So how many grams of hydrogen are in 1 mole? 2.016. Because I take 1.008 and multiply by 2. And then this ratio here, what do I put in front of moles of ammonia? 2. And in front of the hydrogen, so I've got 3 moles of hydrogen for 2 moles of ammonia. 2 moles of ammonia, 3 moles of hydrogen. And then at the end, I need the molar mass of ammonia, 14.01 plus 3 times 1.008, which is 17.034. I've done that one too many times. So before we do the math, let's look at what's going on with the units here. I canceled out all the units except for the gram here and the kilo over there. Is it okay to put those together? Sure. What I'm doing is I'm setting aside the times 10 to the 3 instead of dividing by times 10 to the 3 and later multiplying by times 10 to the 3. So I'm going to end up with a unit of kilograms. Does anybody have any questions about that? Is that okay? Does that make sense to you? Because I don't expect it to make sense to everybody. Some people might be bothered by that or say that's kind of complicated. So what I'm going to do is on the next one where we go from nitrogen to ammonia, I'm going to do it a different way. So you have two different examples. So let's do the math here. 5.22 divided by 2.016 times 2 divided by 3 times 17.034 equals, how many significant figures should this answer have? 3. So what I'm going to do here is I'm going to write down 3 and then 2 extra digits. So there's my 3 sig figs. And then I'm going to write down the 2 next digits. I don't have to worry about rounding or anything. And then I'm going to round it and say this is 29.4 kilograms. So we did half of it now. That's the one ingredient. Now we're going to do the other ingredient. So the other ingredient is the reactant is the nitrogen. So we got 31.5 kilograms of nitrogen. And I'm trying to find kilograms. And so I'm going to do it the long way. I'm going to add a step at the beginning because I'm not starting with grams, I'm starting with kilograms. So I'm going to convert kilograms to grams. At the end I want kilograms, and so at the end I'm going to convert my grams to kilograms. This is the, maybe, the tortoise and the hare. This is the tortoise method. It's slow and steady. It always gets you there, right? So there's nothing wrong with it. So then we've got 1, 2, 3, 4, 5 arrows. So I'm going of kilograms of nitrogen, to grams of nitrogen, to moles of nitrogen, to moles of ammonia, to grams of ammonia, and finally to kilograms of ammonia. Does anybody have any questions about the path? I'm starting in the same place and ending in the same place. Here I started with kilograms and I ended with kilograms. I'm just taking a slightly different route. So then I put my units in again. So I've got kilograms down here and grams. I'm going to cancel these out as I go. Kilograms and grams and moles and moles and grams. So I've got a lot of fractions to put numbers in. I like to start with the easy one, and I think the one in the middle, the mole one, is easiest. Those numbers come from the balanced chemical equation. So up here in front of nitrogen I have the number 1. It's just not written. So I'm going to put a 1 in front of nitrogen. And in front of NH3 I still have the number 2. So I've got 2 moles of NH3. The mole ratio is different here because we're looking at different reactants. There's another one that's easy. This grams of ammonia to moles of ammonia, we use that in the first one. So we don't have to calculate that again. We can just copy it down. So that's still 17.034. I need grams of nitrogen to moles of nitrogen. Molar mass, right? So 2 nitrogens, each 14.01 grams, 28.02 grams. So 1 mole of N2, 28.02 grams. And now I need to do my metric conversion with the kilo, right? So kilo stands for times 10 to the 3. In this first term, in the denominator, I have 1 kilogram. So in the top, I'm going to write 1, but instead of kilo, I'm going to write what it means, times 10 to the 3. When I get to the term at the other end, I have kilogram on top, 1 kilogram, and in the denominator, I'm going to write 1 times 10 to the 3. Because this times 10 to the 3 means the same thing as kilo. Everybody okay? So then you can run this through on your calculator. Now, if you like the first method, you can probably see that you could just take this one, and they're going to cancel out, right? And that's why this first method works. But we're going to do it the long way here. 31, let's start with the right number. 31.5 times 1 EE3 divided by 28.02 times 2 times 17.034 divided by 1 EE3. And I'm going to get, this should also have 3 sig figs, 38.299. Unit there's kilograms, and then when I round that, I get 38.3 kilograms. Everybody okay with that? So what's my answer? What's the theoretical yield? The top one, the smaller one, right? Sometimes, especially this happens on like a post-lab question or a worksheet problem. You've got a problem like this, and you've written all this stuff out. I can't give you full credit for just this. You have to choose one of the answers. So you got to do something to indicate which of those you're choosing. So that's my theoretical yield. That's how much we would get if the reaction went perfectly. What is my limiting reactant? Here's my theoretical yield. The limiting reactant is whatever that one started with. It's the hydrogen, because that's the one that runs out. So we can say that, because sometimes it'll ask you for the limiting reactant. So H2 is limiting reactant. There will be extra nitrogen left over. That's okay. Any questions? Let's do another one. Talk about mining. Mining companies use this reaction to obtain iron from iron ore. Reaction of 167 grams of Fe2O3 with 85.8 grams of CO produces 72.3 grams of iron. Determining the limiting reactant, the theoretical yield, and the percent yield. So it's asking for 3 things. Let's take those numbers and write them under the equation. So Fe2O3, 167 grams. And carbon monoxide, 85.8 grams. And under iron, 72.3 grams. So those are all the numbers. What are we trying to find? We need the limiting reactant. We can't do that first. The theoretical yield is the thing that we can find first, and we need to find that before we can find out what the limiting reactant is or what the percent yield is. Theoretical yield of what? This one has two products. Which one are we interested in? The iron, right? We know that because of this sentence up here. Mining companies use this reaction to obtain iron from iron ore. So we're trying to find how much iron is made, but there's a number under it. Is this telling us how much our theoretical yield is? This is the actual yield. This is saying the reaction of this with this produces 72.3 grams. So the actual yield is something that we have to kind of tell you, or in the lab, it's what you measure. It doesn't come from the calculation. So what I'm going to do is I'm going to set that aside, and I'm going to say that my actual yield is 72.3 grams of iron. And then I'm going to erase this over here. What I'm trying to find out is how many grams of iron can be made. That's going to be the theoretical yield. Everybody okay with that? So I have two reactants, and I'm in a limiting reactant sort of a problem, and so I'm going to do grams to moles to moles to grams twice. So I like to start with the first one, 167 grams of Fe2O3. And what's next? Moles of Fe2O3, grams to moles, and then moles of Fe. Because that's what I'm trying to find. That's like the pizza. And then at the end I want grams of iron. So my general path, grams to moles to moles to grams. That's what's here. Grams to moles to moles to grams. Grams of what I'm starting with to moles of what I started with to moles of what I want to find to grams of what I want to find. And then I fill in the units and the denominators. I get all the units in place, and then I put in numbers. The mole to mole ratio, what do I put in front of moles of iron? 2. And what do I put in front of moles of Fe2O3? 1. This comes from that 2 moles of iron and 1 mole of Fe2O3. I've got 2 molar masses I need. I'm going to do the last one first because that one's the easiest. It's just iron. So I just look it up on the periodic table, 55.85. Double check. Yeah. And then I have to calculate for the Fe2O3. So there's molar mass calculations on the exam, right? Fe2O3, 2 times the mass of the iron, plus 3 times the mass of the oxygen. 2 times 55.85 plus 3 times 16, 159.7. That's the mass in grams of 1 mole of that compound. So 1 mole of iron oxide, 159.7 grams. So 167 divided by 159.7 times 2 times 55.85. This is also going to have 3 significant figures. I'm getting 116, and I'm going to write down 2 extras. So that would round to 117 grams. Any questions? 117 grams. Mm-hmm. Because I'm keeping the first 3 digits, and the first one I'm dropping is the 8, so that makes the 6 round up to 7. Now I need to do this again with the other reactant. Does this seem a little tedious? It is a little tedious. If anyone ever tells you that science isn't tedious, they don't know what they're talking about. Now, science can also be very, very exciting. It's like a lot of life. Isn't life kind of tedious sometimes? There's a lot of waiting around. But we do it anyway, right?
So instead of FU, we do 3CO?
We could do 3CO2, but we don't need to this time because the question is indicating that we're interested in the iron. If we calculated the mass of CO2, we could still figure out what the limiting reactant is. But our theoretical yield and the percent yield would not be quite right. Okay, yeah, so we're going to do the carbon monoxide now. 85.8 grams of carbon monoxide. Are you guys starting to see this pattern here, grams to moles to moles to grams? Because we do it over and over and over again. It's kind of important. So grams of CO to moles of CO. To moles of, I'm going to the same place. I'm going to the same product, iron. And then grams of iron. So I've got grams of CO down there, grams of CO cancels. I'm going to put moles of CO down here. Those cancel. Moles. Say that again? Why does it cancel? So up here I'm using moles of carbon monoxide as a unit, and then I'm going to use it down here as a unit also. And we can treat units like variables. So if these were x's, x divided by x cancels out, right? So as long as we have the same combination of letters on the top and the bottom, they'll cancel out also. So in the middle, see, each of these is a conversion factor, and it's unit conversions, really. What we need is for what's on the top of the fraction to be the same in value as what's on the bottom. And so when we look at this chemical reaction, we see that for every 3 COs, we're going to make 2 FEs. So those are equivalent. Just like we could say that 5 ounces of tomato sauce is equivalent to a pizza. Are they the same thing? No. But in the process of making pizzas, they are the same thing. If you have 5 ounces of sauce, that means you can make 1 pizza. So that's the idea here. So I'm going to put 2 in front of Fe and 3 in front of CO. The last term is the molar mass of iron. I already did that. 55.85 0.85. This is all kind of cramped up down there. And then I need the molar mass of CO. So carbon plus oxygen. So 1 mole of carbon monoxide weighs 28.01 grams. Got my units in place, I got all my numbers, and then I just punch them through on my calculator. Start on the left, multiply by the top. You can multiply by 1 if you want, or you can skip it. Divide by 28.01, multiply by 2, divide by 3, multiply by 55.85, and if you want to divide by 1, it's not going to hurt anything, equals, this will also have 3 significant figures. So there's my 3, and I want to write down 2 extras. And the unit left is grams of iron. So I didn't put it all in the top there. So that would round to 114 grams. So how much iron could be made? 114. We've got 2 answers here. We choose the smallest one, just like we did with the pizzas. So this one is my theoretical yield. So I'm going to single that out somehow, call that TY, theoretical yield. What's the limiting reactant then? It's the CO, because this was my theoretical yield, because this is what I get when I completely use up all the CO. This one, there's going to be some left. So this carbon monoxide is my limiting reactant. You can write the words out, but I know what LR means, limiting reactant. So we've got 2 of the things now. Limiting reactant and theoretical yield. What's the percent yield? So here we need to use an equation. Percent yield is the actual yield divided by the theoretical yield. And then to make it a percent, we multiply by 100. So the number I calculate is my theoretical yield. That's what goes in the denominator. I don't want to use this rounded one though, because I could end up with some rounding issues. So I'm going to use this one, which is just sitting there waiting for me. I didn't have to recalculate anything. So I'm going to put 114.05 grams in the bottom. That's got 3 significant figures. And the actual yield was given to me. In a problem like this, it pretty much has to be given to you, because you have no other way of figuring it out. It's like if you're making pizzas and you say, well, I had enough stuff to make 15 pizzas. How many pizzas did I actually make? You have no idea. Maybe I had a good day and I made 15. Maybe something really awful happened and I only got 1 made. The only way you can know is if someone tells you. And so that's how the actual yield is. So actual yield over theoretical yield times 100. I see a funny thing happening when students are calculating percentages. You write this out, you do this division, and then you don't actually multiply by 100. And I think there's a couple of different things that can happen. A lot of times the equation says 100%. That does not mean you should push the percent button on your calculator. That's not what that means. This percent here is the unit, because you see what happens with these units? The grams cancel out. That's always going to happen in a percentage. So you end up with this unitless thing times 100. Think of this as the unit. So I've got 72.3 divided by 114.05. before I multiply by 100, that's 0.6339. I need to multiply by 100, and my answer should have 3 significant figures, so I'm going to write down 5 of them. So 63.393% is the unit, and then I'm going to round it and call that 63.4%. And there is my percent yield. Any questions? This is a very practical sort of calculation, because this tells the mine company owner or manager that, hey, we're wasting resources here. We're only getting 63% of the iron out of this ore that we could be. So maybe we should look into how to make this process give us a higher yield. We can make more money that way.